In part 1 of our split flow setup guide, we went over how to generate the mesh files necessary for running the split flow simulation. In part 2, we'll go over what's required for actually running split flow simulation. To begin with, we'll list some of the prerequisites that are required. We'll then take a look at the process overview. And then we'll talk about, what is an MPI table and what's required from our MPI table by looking at the MPI table structure. And finally, we'll look at some split flow specific setup guides for the MPI table. So to run a split flow simulation, the first thing that we need are restart files, or a mesh for each row that we intend to simulate. The generation of these is described in part 1 of our split flow setup guide. The second part is that a .leo file is required for each individual row that we intend to run. Specifically, the fan should always be the first .leo file that we specify. And then depending on whether or not we want to run a bypass or a core speed line using the workbench, the last row should be defined as either the bypass or the core, respectively. Finally, the MPI table, which is what we'll spend most of our time on in this presentation, should be specified in the first .leo setup file. And this is going to describe our multi-stage communication. Each row interface is going to require an entry in the MPI table. This will automatically be created in future releases, but any users running 6.83 or earlier need to create this manually. As we mentioned before, for each row, we're going to need a restart file. So you can see here, going into Leo, we have a fan restart file, a splitter restart file, an exit guide van from the fan or bypass restart file, and one or more core restart files. In addition, we need .leo files, which will tell the solver how to run the simulation and which restart files to point to. So what is an MPI table? The MPI table is what defines the inter-process communication when we run simulations in parallel. It's essentially describing the interface between all of the rows and or passages and how communication occurs across those interfaces. What we're seeing on the left-hand side of the screen is an example of the first Leo file in a parallel simulation. The first 3 rows are pretty standard, what we would see in a .leo file, with the exception being that the third entry on the second row, prun, is set to 3 rather than 0 or 1, which is what we would normally see. When we set prun to 3, what that tells the solver is that the user will be manually specifying the MPI table. The MPI table is then included after the first 3 rows at the bottom of the .leo file. The first entry in the MPI table, as highlighted with the orange box, tells us the number of inter-process boundary conditions. So what is an inter-process boundary condition? An inter-process boundary condition is an interface between 2 rows and or passages. So going back to our split flow mesh setup case, we have our fan, our splitter, our bypass duct, and our core. So in this scenario, we have three interfaces between adjacent rows. One between the fan and the splitter, another between the splitter and the bypass, and then a third interface between the splitter and the core. So for each of these interfaces, or inter-process boundary conditions, we have three rows in the MPI table. The first row has three entries, where we describe the inter-process boundary condition type, and this can be either a mixing plane, interpolation, or a point-to-point match, as well as the number of entries on either side of the interface. Now for our split flow setup, we'll always have one entry on either side of the interface. So these last two entries will always be 1 and 1. So if we look at the one of these inter-process boundary conditions in detail, we'll start by looking at the interface between the fan and the splitter. So the first thing to notice here is that we have these numbers in gray boxes associated with each of these. These correspond to the MPIDs for each row. An MPID is an integer that labels that's used as a label for each row. So in this case, the first row, the fan, is set to an MPID of 101. The second row, the splitter, is set to 102. The bypass is 103. And the core is 104. So we already described the first row in our inter-process boundary condition. Here, we're using a mixing plane interface. Again, we're always going to have one entry on each side of the interface for our split flow setup. We can then move to the second row for the inter-process boundary condition. And here, we're describing the MPID on one side of the interface, as well as the CFD boundary condition type on that side of the interface. So here, we're looking at MPID 101, which is associated with our fan mesh. And as you can see, the interface here is on the exit plane of the fan, or the upstream face of the splitter. Since we're looking right now at the downstream, or the exit plane of the fan, our CFD boundary is type 6, which corresponds to a non-reflective outflow condition. Looking at the next row, which corresponds to the opposing side of the interface, our MPID is 102, which corresponds to our splitter mesh, and our CFD boundary condition is type 5, which corresponds to a non-reflective upstream boundary condition. Moving on to the second interface, we're looking at the communication between the splitter block and the bypass duct. So again, in the first division, we can see that the communication type here is a mixing plane. However, it's important to note that we can also run an interpolation type inter-process boundary condition with two requirements when we run steady flow. One is that the number of airfoils or blades in the adjacent rows must match. And two is that the frame of reference must be the same between the adjacent rows. Moving on to the second row, again, we're looking at the splitter side of the interface. Our MPID is 102, which corresponds to the splitter. And then our CFD boundary condition is set to 4. This is a special case where for the exit condition that feeds into the bypass duct for the split flow setup, we should always set that boundary condition to 4. We wouldn't do that in a normal scenario, but only for the splitter mesh feeding into the bypass duct, we should always set that boundary condition to 4. On the bypass side, our MPID is 103, which again corresponds to our bypass duct. And then our CFD boundary condition is type 5, which corresponds to, again, a non-reflective inlet condition. Finally, looking at the interface between the splitter and the core, again, we have a mixing plane type condition. Our first entry is MPID 102, which tells us that we're looking at the splitter side of the interface, and our CFD boundary condition is type 6, which corresponds to a non-reflective outlay type condition. The other side of the interface, the MPID is 104, which corresponds to the core, and then our CFD boundary condition is type 5, which corresponds to a non-reflective inlet condition. So here again is a sample of the first .leo file for our sample split flow case, including the completed MPI table. This can be used as a template for any users wishing to set up their own split flow simulation. Thank you for listening to our split flow setup guide. For more information, please go to adscfd.com.